The next thing is LaPlace's law, and so here's the equation right here. T equals PR divided by W. So T is wall tension, P is transmural pressure, R is radius, and W is wall thickness. And so one thing just I want to point out before I start here is that that is actually the equation for a tube. So it's a little bit different with the heart, but I think the main thing to know is the R over W relationship, so which is illustrated here on the diagram. So if you look here, you can see that passively filling the heart with volume, you're going from here to here, and so you can see here's the volume before the atria starts putting blood in, and then here's the volume afterwards. And so you can see that the thickness of the heart wall has decreased, whereas the radius has increased. So and these circles aren't perfect, but I think you get the general idea that so we get to here, and that's when the heart starts to contract. And so right now the pressure inside of the heart here is low, but you have your isovolumic contraction going this way, and the pressure inside the heart goes way up. So what happens is here the ratio of the radius to the wall thickness ratio is the highest because the radius is large and the wall thickness is very small. So here you have this is the most tension, wall tension, and another thing that I should mention is tension is actually if you think of a tug of war, so you have people here playing tug of war, somebody with no arms there, I'll put some arms on them, and somebody here playing tug of war and pulling this way and this way. Tension is being experienced in the rope right there. That's what the physical property is. It's tension. And it's actually, the units of tension, I believe, are newtons, which is force, but it's not technically a force. So, but tension is very significant for things like blood vessels and for heart walls because those things can rupture based on tension. So that's the relationship that you want to understand, is that as the heart expands, this ratio, the R to W ratio, is going to be increasing because the wall is going to be getting thinner because it's getting larger and more blood's going in there, and the radius is going to be getting larger because the heart's getting larger. These diagrams aren't wonderful because I didn't change the size of the circle, which I probably should have. So anyway, and then these black lines are supposed to represent contraction. There's no contraction happening right here at end diastolic volume or preload, and then the contraction starts right after that, and then this would be the heart contracting as hard as possible, and then here at the PIP, peak isovolumic pressure, once again, I'm going to draw on the PIP line, the heart should just, the valve has closed, the aortic valve has closed, and now we're going to take away some of this active contraction. We're going to have isovolumic relaxation, but still the maximum that the max tension on the heart wall is going to be at this point right here every single time, and it's because of this equation right here. And this equation is, again, this equation is for a cylinder, so you can think of it more as far as like a blood vessel or something like that. And so I think a really good application of this equation would actually be an aneurysm. So if there's an aneurysm in a blood vessel like the abdominal aorta, this would explain why at the same pressure inside here, the wall tension is going to be higher. And that's a really bad deal for an aneurysm because then, an abdominal aortic aneurysm is more prone to tear, which is a disaster. But as far as the heart goes, the same relationship with this, still applies. I think that there's probably supposed to be a 2 up here, but don't worry about that. It's not exact. Just the main thing to know is just, to be able to apply this principle that as the width gets lower and as the radius gets larger, the tension is increasing and the max tension will be experienced right here. Okay?